So I'll be talking a little bit about how we accomplished acquiring data sets through CT scanning. You can see here images of each of our two CT scanners that we have in our lab, two Zeiss scanners, a Metricon 800 and a Metricon 1500. Each scanner operates in a different energy and size regime, which allows us to complement different parts nicely. So if we look at this diagram here on the left right now, we can look at how the inside of that machine is laid out and the basics of how the data set is acquired. So on the left here, we have an X-ray source. On the right side of the screen, there's a flat panel detector. And in the middle is your workpiece that goes onto a rotary stage. And during the course of the scan, that rotary stage rotates through 360 degrees to acquire different cross-sectional images of the part, which are then reassembled into a 3D data set. Now, the part can also move in the y-axis there. And as you can see, as you move away from the X-ray source, the image got smaller, and now as you go closer to the X-ray source, the image gets bigger on the source, or excuse me, on the detector. And this is important because it's important to talk to a CM provider about what sort of resolutions are required for your particular project. So, what do we mean when we're talking about resolution? It's the size of the feature you can see, and also what would be appropriate for whatever tolerances you're working. So if we look at this image here on the left, on the bottom is an idealized shape of sharp corners. And on the top is what you start to lose if you don't have the kind of resolution you need to achieve in your scan. So how do we achieve this resolution? Well, as we talked about earlier, we can move the part closer to the X-ray source, and this allows us to basically increase the size of our shadow across the sides, or across the whole detector, versus if we were to move the part much further away from the X-ray source, we would reduce the size of our shadow. Now, why is this important? That's that each one of these little boxes here represents a pixel on the detector, because our pixel size is fixed. So if we can't move our pixel size, what we can do is stretch our image over more pixels so that any particular area is being described by more and more pixels, subdividing how much area of that curve you can describe. So now we can talk a little bit about the deliverables we offer off of the 3D scan data, in particular the CT scan data. Oftentimes we have customers that just like our CT scan data quality, and we will offer them, they ask us just to give them a scan and an STL file. Maybe they have their own 3D measurement software in-house and they want to do their own measurements. So oftentimes we will deliver an STL like the one seen here. Additionally, we offer full reverse engineering services. We produce surface wraps or fully parametric CAD models. We also do full layouts, partial layouts on our CT scan data. Another common deliverable, either standalone or with a layout, is a CT scan and a color map. And in this case, you have some sort of nominal object, be it a CAD model or maybe another part, and you overlay your CT scan data onto that other model, and then you can map all the different deviations across the whole part to the corresponding areas on your nominal object. This will give you a great idea as to the size and form of your part that you're currently making. Additionally, we can do porosity. Since it's an X-ray technology, we're gathering data all the way through the part. So if we do a kind of digital cross-section here, you can see all these different pores that have been quantified within the part. According to some color scale, usually effective diameter, probability, or volume encapsulated in the pore. Additionally, we can offer services like wall thickness analysis and assembly and defect analysis, and there's a whole host of other services. These are just some of the common ones.